Welcome to this video in the electrochemistry topic, our second on predicting reaction feasibility. And I'm going to introduce you the idea here of the expected cell potential. And we're going to calculate that for reaction, and we're going to understand how this can be used to predict reaction feasibility. So I want to start off by introducing to you an alternative way to calculate the cell potential. In previous videos we've said that to calculate the standard cell potential from two half cells, we simply do the standard electrode potential for the positive electrode, subtract the standard electrode potential for the negative electrode. So it's the potential difference between these two values. Now, what we found out in the video on cell reactions is that at the positive electrode we tend to get reduction happening. We do get reduction happening. So this species here, the copper 2+ ion, is getting reduced. In contrast, at the negative electrode we have oxidation happening, and the zinc becomes oxidized. So we can equate the standard electrode potential of the positive electrode to the standard electrode potential for the reduced species, copper 2+ in this case. And we can equate the standard electrode potential at the negative electrode to the standard electrode potential of the oxidized species. Okay, now let's think about why this is useful. So I've just put the equation up here. We're going to consider this reaction between chlorine and bromide ion, which in the previous video we showed was a feasible reaction. So let's try and see what happens then when we use this formula. So what we find here is that the species that's being reduced, we looked at the oxidation numbers, and we found out that it is chlorine which is being reduced, and bromine is being oxidized in this particular reaction as we've drawn. And so essentially what we can say here is that because chlorine is being oxidized, chlorine is being reduced, this is a standard electrode potential for the reduced species, and this is the standard electrode potential for the oxidized species. Now it's really important, if you're following this method that I'm doing, that you never ever flip any signs of these. Now I know that the reverse reaction is happening here, but don't be tempted to put a minus sign here. You will get it wrong. So we just follow what the formula says, and we can calculate E standard cell as 1.36 subtract 1.09, and we get from that 0.27 volts, and it's positive. So that's really important. So for this feasible reaction we've got a positive cell potential. Okay, let's calculate the expected cell potential for this iodine-bromine reaction, which in the last video we showed was not feasible. Let's see how things change. So again, it's a very similar reaction. We've got the iodine here being reduced. So this is E standard of the reduced species, and the bromine is being oxidized, and so we could say that this is E standard for the oxidized species. So again, we plug the numbers into the formula, and we find the standard cell potential that's predicted from this reaction is going to be 0.54 minus 1.09, which comes out at minus 0.55 volts. So notice negative for an unfeasible reaction. Okay, and in fact this turns out to be very general. So what we find here is that if E cell for the reaction as written, so E cell is greater than 0, that implies that we've got a feasible reaction. In contrast, if it turns out that E cell is less than 0, then we've got an unfeasible reaction. Okay, now that rule is something that you can learn and apply, and you can do so very happily. I'm just going to spend the next couple of minutes just explaining why it works. So consider the cell formed between bromine and chlorine. What you're essentially doing with these E-cell calculations is that you're saying we want in our reaction, let's just remind ourselves of the reaction, 2Br minus goes to 2Cl minus and Br2. Now in that reaction we want chlorine to be reduced, and so basically what we're saying is because we want chlorine to be reduced, we're going to set chlorine as being the positive electrode, and because we want bromide to be oxidized, we're going to say that that's going to be the negative electrode. Now if we do that and we find, as we did here, this is plus 0.27 volts between these two, the potential difference, then we were correct in putting chlorine as the positive electrode, and therefore this reaction will happen as we thought. However, in the case of bromine and iodine half cells, we again said we want iodine to be reduced, so that had better be the positive electrode because that's where reduction happens, and therefore the bromine or bromide which is being oxidized is going to have to be the negative electrode. However, when we do that, we find that the potential difference is actually minus 0.55 volts. So what that means is that we were just wrong to put iodine as the positive electrode. Actually, it should be the negative electrode. But if it's the negative electrode, of course, that means that oxidation will happen. So we would tend to get the equilibrium shifting towards the left and more iodine being produced. And so the upshot is when we actually calculate E cell for the expected reaction, we get a negative value. And all that is meaning is that actually our positive and negative are the wrong way around, and therefore the reaction we want is not actually going to happen. In fact, the reverse reaction would happen. So just to summarize, for any redox reaction, and there's an A there, for any redox reaction you can calculate the expected cell potential in this way. And this is a valuable predictor for reaction feasibility because if it's greater than 0, it's a feasible reaction. If it's less than 0, it's an unfeasible reaction. So as long as you can work out from your equation which species is being reduced and which being oxidized, you can use this prediction to work out whether a reaction is going to be feasible or not.